So we are going to talk about Bayesian networks, which is the scalable method to encode these joint probability distributions. And in the first part of the lecture, we are talking about the representation and the semantics. And then we will talk about exact inference, approximate inference, and learning. It's a handful, we'll not complete everything today, but hopefully we'll complete at least the exact inference part and maybe even approximate. What Bayesian networks does is that essentially it is computing these joint distributions, nothing more than that. But reducing the exponential number of variables or exponential number of parameters that are needed to encode a complete joint distribution by creating a graphical representation that encodes the conditional independencies that we know in our model. And by exploiting these conditional independencies, we are able to make this representation much more compact, has much fewer parameters, and the inference can be done usually relatively efficient. That's the goal. So this was, so if I had to create a Bayesian network, this is just a quick trailer. If I had to encode the Bayesian network that we just discussed, or the network that we just discussed, we will say that weather is an independent variable, cavity, toothache, and catch are dependent, and toothache depends on cavity, and catch depends on cavity. It is easier to think about Bayesian network in coding causal processes. I should also give you the caveat that Bayesian network doesn't have to be causal. If there's an edge from one node to the other node, that edge doesn't imply that the first node is the cause and the second node is the effect. However, it is intuitive for us to think about it that way, at least in the beginning. So what happens is that each random variable has a node. It's a directed acyclic graph, and an edge indicates that I will have some notion of what is the probability of the second variable given the first variable. This particular structure is actually encoding the same fact that toothache and catch are conditionally independent of each other given the cavity. And by the end of the class, you will hopefully start to identify how to make these conditional independences by looking at the structure of the Bayesian network.
Question. In the previous slide, how do we decide which way the arrow is?
This is just a trailer, as I said. We're going to talk about it a lot. So syntax is a set of nodes, one per random variable. It's a directed acyclic graph. The idea of a link is some notion of directly influences or causes, and additionally associated with each node, we will have a conditional distribution, or a conditional probability distribution, or a conditional probability table. It goes by CPT, CPD, all of those. Okay? And the idea would be that it would encode the probability of the node given all of its parents. And we'll give you examples in a minute. This is exactly the network that we just discussed. It has burglary, earthquake, alarm, John calls, and Mary calls. By the way, I should have said that when we described this example, but the reason this example said Pearl in Los Angeles is because Julia Pearl is an extremely distinguished professor at UCLA. In fact, he won the Turing Award last year. I hope you know about Turing Award. Yeah. It's the Nobel Prize in Computer Science. He won the Turing Award last year for his pioneering work in Bayesian networks, causal reasoning, and etc. in the context of AI. So this has been incredibly influential, which you may anticipate just by this piece of information. So Julia Pearl, this is probably his example, or at least an example for him. So this is my Bayesian network, and I think I have shown you, but if you had to write this Bayesian network, you would probably write this Bayesian network yourself. So you will say, that earthquake can happen and burglary can happen. And alarm goes off depends on earthquake and burglary. Right? If earthquake happened, then alarm will go off. If burglary happened, then alarm will go off. If alarm went off, then what will happen? John will call, or Mary will call, or both will call. So basically, John calling depends on the alarm, Mary calling depends on the alarm. So this notion of the edge is directly influences. Again, you're getting the intuition, right? Now, let's talk about the number of parameters. How many here? How many here? How many here? This is tricky. Sorry, the question was, how many here? My bad. For alarm, I'm asking for alarm. So how many parents does it have? Two. Each parent has two values. So what are the possible values of the combination of parents? For each variable, for each of those combination, we will have to have a parameter. So 4 sums to 1, so 3. Similarly, how many here?
Given the alarm will jump home.
1, 2, 3, 4. Alarm can be true, or alarm may be false. And for both of these, we will have a parameter for John calls. So 2 here, 2 here. So we're talking about 2 plus 2, 4 plus 3, 7 plus 1, 8 plus 1, 9. 9 parameters for a Bayesian network with 5 variables.
Question. So alarm will be true John calls, and alarm will be false John calls. 2.
Precisely. Let's look at the values. So this says that probability of earthquake can occur with probability 0.002. This says probability of burglary is 0.001. This says that probability that alarm goes off depends on both earthquake and burglary. So if both earthquake and burglary happened, then alarm will go off with probability 0.95. If earthquake happened and burglary did not happen, then alarm will go off with probability 0.29. If burglary happened, earthquake did not happen, then alarm will go off with 0.94. And if none of them will happen, then by chance alarm will still go off with probability extremely low. Similarly, John calls, John will call if alarm goes off with probability 0.9. John may have drunk, so John may call when alarm doesn't go off with probability 0.05. Similarly, for Mary. Total of 9 terms. Okay? So this is the knowledge that is given to us. This is a full encoding of the Bayesian network with these 5 variables, encapsulating all our intuitions about this domain. Any questions? Everybody okay?
How are you counting the parameters?
1. Because this is dependent on this. Because this sums to 1, right? 1, 2, and then 4 of these. Yes, 4 of these. So I made a mistake by calling it 3. 4 of these, 2 of these, 2 of these. 10 parameters, not 9. Thank you.
A little second.
Exactly. Yeah, my mistake. So, okay. Now, if we know alarm, does it, if we know alarm, if we know that alarm went off, then probability that John will call, does it depend on earthquake? See, once alarm goes off, it really doesn't matter whether earthquake happened and caused the alarm or burglary happened or caused the alarm, John is still going to call with the same probability distribution. So by knowing, given that alarm has gone off, knowing earthquake does not give me any new information about whether John is going to call or not. So therefore, in conditional independence terms, what can we say? Given alarm, earthquake and John calls are conditionally independent.
But he could feel the earthquake, so.
Given the model.
If that was true, would we would draw an edge from earthquake to John calls?
Yes, absolutely. So that means, in fact, here is another one. If alarm went off, does it matter whether Mary called or not for John to call?
This one.
John has nothing, it doesn't matter whether Mary called or not. John is going to call just based on the alarm itself. So therefore, in some sense, John calls is independent of everything else given alarm. Similarly for Mary calls. So equivalently we can say John calls given all other thing is equal to John calls given alarm. Similarly, Mary calls given everything else is Mary calls given alarm. Moreover, if I knew burglary occurred, does it change the probability of earthquake? So in other words, earthquake and burglary are independent of each other. They're not given anything, they're just independent of each other. So now, by the chain rule, if we use the joint distribution, so joint distribution is probability of all these 5 variables, then by using product rule, we can say that this is probability of B times probability of E given B, probability of A given E comma B, MC given A comma E comma B, JC given MC comma A comma E comma B. But probability of E comma B is same as probability of E because E and B are independent. Probability of MC given everything else just depends on alarm. Probability of JC given everything else just depends on alarm. So we get this factorization of the joint distribution. And did you observe something? This is exactly equal to multiplying the conditional probabilities along each edge for each node. So probability of B is this, prior probability. Probability of E is here, prior probability. Probability of A is given B comma E, given its parents. Probability of John calls is given its parent. Probability of Mary calls is given its parent. In fact, we can generalize this and say that for any Bayesian network, the joint probability distribution is a product of factors where each factor is probability of a variable given its parents. This is the operative principle.
So what does the joint distribution represent? Probability that they're all true?
No probability, they are all a certain given value. So it could be probability John calls, Mary did not call, alarm went off, earthquake did not happen in burglary.
Probability of a particular outcome of the law.
Probability of a particular atomic event.
Probability of one set of assignment.
Probability of a state. No question. So this is the operative principle, and that is what makes Bayesian networks so pretty damn awesome. That it's just as the simple operative principle that if I drew my Bayesian network right, I can compute joint probability just by going along each node and multiplying these factors. Now, let's deep dive into conditional independence for the next few minutes. So the first rule that I'm going to teach you is called local semantics, or it is a local semantics rule for Bayesian networks. It is that X is conditionally independent of all non-descendants given its parents. Yes.
Question on the previous slide. So, like, when you said like does burglary depend on earthquake and so on, so based on our understanding of these things, we said yes or no. But from the graph, if there is no edge between them or it's not on the path, then we can say they are conditionally independent.
You're running ahead of me. Give me 10 minutes and you will get your answer. So, the first rule that we will learn is that given its parents, a node is conditionally independent of all non-descendants. So, let's try this in an example. This is an example. So, it says, given u1 to um, X is conditionally independent of all non-descendants. So what are the descendants? Y1 to yn and anything that happens down. what are the non-descendants? Z1, Zn, and anything that is above U1. Okay. So let's do it in our example. So given alarm, what is John calls, actually what is given here? Yeah, I think that's right. So given alarm, what is John calls conditional independent of? What are the descendants of John calls? So what are the non-descendants of John calls? Earthquake, burglary, and Mary calls. So essentially, John calls is conditionally independent of all these three given its parent, which is alarm. Okay, first application of the rule. Is it intuitive? We have seen this again already, right? That once we know alarm, whether earthquake happened did not matter, whether burglary happened did not matter, whether Mary call did not matter. Here's another example. Given earthquake and burglary, what is alarm conditionally independent of? Okay, so you use the rule just fine. Is this true, by the way? Is it conditionally independent of radio, John calls, and Mary calls? No. So the right answer is radio. Okay. So now you use the rule fine, but let's make the intuition because it's not just applying the rule. What is happening? I know earthquake, I know burglary. Why is alarm not conditionally independent of John calls? What is the intuition? Is John calls giving me new information about alarm?
Yes.
It's an effect of alarm.
Right.
So if John is calling, it's more likely the alarm is actually happening,
Exactly.
whereas radio doesn't have that effect.
Exactly. By knowing that John called, there's a good chance that alarm actually happened. Even if earthquake and burglary did not happen, for example. So I am getting new information. So that is exactly what Bayesian network is encoding. It is saying that the descendants actually tell something about the cause, and therefore I can't be conditionally independent of the descendants, but I can be conditionally independent of the non-descendants.
What we're saying is, you know what happened with earthquake and burglary.
Precisely.
And the fact that John called allows you to understand if
It just gives me new information about predicting whether alarm went off or not.
If you know about all the parents, why would you need
The children.
information from that descendant?
That's what we were discussing.
well, there is a 1 in 1,000 chance that alarm would just go off even though earthquake and burglary did not happen from the numbers.
Here's an example. Suppose earthquake happened. Burglary did not happen. Right. Earthquake happened, burglary did not happen. What do we know about alarm right now?
There's a 20-something%.
There's about 24% chance that alarm is gonna go off. Now if I know that John called, don't you think that it's even more likely that alarm would have gone off? Because John has a very high probability of calling if alarm goes off. And very low probability of not calling.
Yeah,
Very
it's-
high probability of not calling if alarm did not go off. In fact, let's suppose both John and Mary called.
I thought you said alarm was given.
Alarm is not given.
Alarm parents are given.
Earthquake and
There's a
burglary.
probability distribution given to parents of the state of alarm, but now we want to predict alarm, we get even more information if we know that.
Precisely. So the intuition is, am I getting more information about something? And by observing an effect, I usually get information about the cause.
That's the base.
That's the base theorem also came from.
Basically, John and Mary are telling you if your alarm works.
Yeah.
You
You
know
had
what
a
happened,
stiff neck,
your
so it's
alarm
more
worked.
likely you have meningitis.
Precisely.
So what are non-descendants?
Non-descendants are one that are not the descendants. So that means parents of the parents, other children of the parents, their children.
Parents of parents. But parent is a non-descendant. It's not a non-descendant.
Parent is already known to us, so it doesn't matter. But parent is also a non-descendant, for sure, yes.
Is there any additional assumption here that John calls and Mary calls are not descendants of any other parent?
No. So as long as they are descendants of Alam or further descendants here, even if they come from an alternative age, it doesn't matter. Let's do another one. Alright, so this is as much as I was going to talk about the local semantics. But now let's talk about the global semantics. So this is interesting. It says, a node is independent of everything if I know my immediate family. And what is my immediate family? My parents, my children. I'm not just talking about descendants, just children, first level children, and the other parents of my children. This is so true in reality, bro. But so this is called the Markov blanket. It says that Markov blanket is my parents, my children, and other parents of my children. And if I know this blanket, then everything else is independent. It doesn't give me new information. Let's take an example.
Usually actually independent or conditionally?
Conditional independent, of course. Given my Markov blanket. So, what is the Markov blanket? Okay, so is this true? Am I conditionally independent of everything given burglary for alarm? Right? This is not my Markov blanket, so this is not true. What is my Markov blanket for alarm?
Everything is radio.
My children, my parents, and there are no other parents of the children, so everything but radio, precisely. Yeah. Here's another example. Burglary. What is the Markov blanket? It's children and the other parents of the children, so earthquake and alarm. Now again, let's think about intuition. Intuition is the more important. I know alarm has gone off. At this point, does knowing burglary tell me something about earthquake? Or knowing earthquake tell me something about burglary?
Yes.
So earthquake and burglary, which are two completely independent events, right? I mean, what is the connection between earthquake and burglary other than riots, which we're not getting into? Completely independent event. But by knowing alarm went off, they are no longer independent of each other. Why? Because if I know burglary happened, then it reduces the chance of earthquake, and if I know earthquake happened, then it reduces the chance of burglary, and if I know that earthquake didn't happen, then it increases the chance of burglary. In other words, two completely independent causes which have the same effect. By knowing effect, they are no longer independent. First, think about the intuition about Markov blanket. So now burglary, Markov blanket is earthquake and alarm. By knowing John calls, am I getting additional information about burglary? If I already know alarm, then John calls depends on alarm and its after effect, but John calling is not giving me any additional information about whether burglary happened or not. Alarm is giving me good information. So, again, this is the intuition of Markov blanket. And now let's get into, now these are specific rules, right? So I said given parents, I am conditionally independent of my non-descendants. Given Markov blanket, I am conditionally independent of everything else. But I haven't still taught you a general rule which says if I want to test the conditional dependence of two variables given some evidence variables, is that conditionally dependent or not? So now I'm going to answer Abhishek's question as to what are the rules for identifying these conditional dependencies, and the theoretical concept that we will have to learn is called deseparation. The first time I was taught deseparation, I had no idea what was happening. It was very confusing. I'll try my best to go slowly and explain. But I really encourage you to go back, to read the book on that particular section at least, and think about it. Because until you think about it, you won't get it. So we are going to find an undirected path between two nodes. And we will say that an undirected path between the two nodes is cut off if information cannot flow from one path to one node to the other node. There's somewhere the path is getting cut off. Okay? So the arrows don't matter. We're just going through a path, and if we can influence, we keep going, we keep going. If our path is blocked somewhere, then we are stopped. We can't go further. And the path tells us what is the flow of information, what is the flow of influence. Okay? Two nodes are deseparated if there is no path that is still active. So all paths are cut off. Okay? And we can generalize this if two sets of nodes are deseparated, if every pair of nodes are deseparated. That's less important. Now, what are the rules for deseparation? Given B, can I have influence from A to C? I try to go from A to B, but I know B. So that influence is cut off. By knowing B, A and C are no longer influencing each other. So if I have a linear path in the same direction, the information can only flow as long as I don't know anything. All of these are unknowns. As soon as I know something, information cannot flow further. So by knowing the variable B, I have cut off this path. Is this intuitively okay?
What if you know B with a certain probability?
No, knowing means knowing. Given B means I know B. By knowing just a probability distribution, I already know some probability distribution.
That's what's given to you.
That's anyway given to us.
Of having the Bayesian network.
So this is cut off from A, right? So let's say there was a D at the end too.
Yeah, same here. So
And
I will try to go from A to D. I will not be able to go cross this. C and D may be influencing each other, sure.
So from B to D still it may not be a cutoff.
No. C to D will not be cut off.
No.
B is known.
B to D.
B is known. So
Yes,
there's nothing happening.
So,
Now, yes.
So this is just basically applying the first rule, which is that C will be independent given its parent.
Precisely. But even if this was a longer chain, then this will still work, as we just discussed. So in this example, by knowing alarm, John calls and burglary are conditionally independent of each other. Now let's do this particular one. Can we flow the information from A to C through B if we know B? Right? This is the cause, these are the effects. Once we know the cause, the effects become conditionally independent of each other. Same example is John calls and Mary calls. By knowing alarm, John calls and Mary calls then become independent. So this is exactly the same principle. Even if we have a diverging connection, I can go from A to C only if I don't know B. If I know B, I cannot go, my path is blocked. Okay? Now comes the tricky one. This is the converging connection.
again.
If I don't know B, what do we know about A and C? They're independent,
You don't know B, they're independent.
No.
right? Because of like earthquake and burglary are independent of each other.
We don't know.
But if I know B, then they are not independent. Because now there are two causes to the same effect, and but as soon as I know the effect, the cause ceases to be independent. So, in this scenario, in the converging connection case, what happens? That information can flow between A and C only if we do have evidence, either in B or any descendant of B. Yes?
Can you give some more intuition on the previous example? Why, knowing that there's an alarm, means that there earthquake and burglary could be related?
Yes, absolutely. And we talked about it, and let's do this again. Knowing that there is alarm makes burglary and earthquake related. Why? Because suppose there was alarm. Now by knowing earthquake happened, I reduce my probability that burglary happened. Or by knowing that earthquake did not happen, I increase my probability.
Oh, you mean, so, okay, so what you're saying is that knowing that there's an alarm changes what could happen if you know about one of the other variables.
Precisely, if multiple parents, multiple causes are causing an effect, and effect occurred, or did not occur, doesn't matter, but effect occurred, then those causes are no longer independent, because by knowing one cause is the real cause, I reduce the probability of others. By knowing one cause is not the cause, I increase the probability of the others. Kim, you had a point to it? Yes.
So what is the de-separation law? Because the way it was stated was counter to this particular example.
No, so I'll just revise the separation rules. You have a question?
So going back to the other one where the alarm and Mary call John law, I think even so, knowing the alarm, the independence, even if we don't know whether there's an alarm or not, there's still independence.
John and Mary?
Yeah, isn't it?
John and Mary are not independent if they don't know that. Why? Great question. Is John calls independent of Mary calls? If we know that John called, does it not make it more likely that Mary is going to call?
Because he most likely called because there was an alarm.
Because John
It's
most likely
because of
called
the-
because there was an alarm, and therefore Mary is also going to call. But by knowing alarm, now these are two independent processes. Alarm went off, now John is going to call by his own probability distribution, Mary is going to call by his own probability distribution. Knowing John called does not affect whether Mary called.
So the fact that first when we mentioned that when B is not known, there's no intuition, or there's no, that doesn't affect either the A or C.
Exactly, there are multiple independent causes to B.
It seems like the semantics are very important in this, like, they're still independent, but they're not conditionally independent at this point.
A and C are independent of each other if we
I was
don't
thinking
know.
of John and Mary, but John and Mary are independent, but they're not conditionally independent.
John and Mary are conditionally independent of each other given alarm.
But even when we do know alarm, they're still independent variables, but they're not conditionally independent once we know alarm.
Exactly the opposite. So, given alarm, John and Mary are conditionally independent. But if we don't know alarm, then John and Mary are not independent. They depend on each other. You get that? So if I don't know
But
alarm,
there's a difference between dependence and conditional independence, or conditional dependence.
yes, the difference is whether we know something or not. Is there some evidence known or not known? So conditional independence is independence given additional independence, or additional evidence. Intuitively, there is no other difference. So, in other words, let me revise this. I don't know anything. John called. High probability that Mary is going to call. They are not independent. However, alarm went off. Now, John's calling and Mary's calling are independent procedures. Earthquake and burglary, a priori independent. Nothing to do with each other. But as soon as alarm went off, earthquake and burglary become dependent, because by knowing one I reduce the probability. So this is that case, this is the convergent case, where there is one effect, multiple causes, and there the influence flows from one cause to the other cause only when the intermediate node is known. And all its descendants are known. Descendants is important. Suppose I know E, it's still, there is still evidence, because is essentially depends on D essentially depends on B, and so this path is still right. Again, I encourage you to think about this a little bit more at home, because this is somewhat subtle, and it takes some time to get yourself internalized with this notion of flow of influence in a Bayesian network. Yes?
So in the previous example, if we know that John called, and that's all information we know, that actually could increase the probability that the alarm went off.
Yes.
And that could affect both either an earthquake or
Yes.
burglary happened.
Yes.
So not only if any of the children of alarm went off, that that still makes a path between.
Right. So we can go from John calls to burglary using this deseparation rule, which is linear.
Okay.
And we can go from John calls to Mary calls using this rule, which is divergent.
Yeah.
And we can go from earthquake to burglary using the convergent rule if we knew alarm is on, or John, or Mary, any of those. Right? So this rule actually encapsulates everything, but we have to make some more intuitions about it. And I think this is as much as I want to discuss in the class, because we should move on. It's not unintuitive, but it's subtle, so you'll get it if you think a little bit.
If you that rule said if John calls, then you can go from earthquake to burglary.
Yes, absolutely. And that is true,
John
right?
might have influenced alarm.
If John called, most likely alarm happened, and if alarm happened, then earthquake and burglary are no longer independent. Precisely. Okay. So the next thing that I'm going to discuss is construction of Bayesian networks. So what we have to do is that we have to choose some ordering of variables, and given the ordering of variables, we can construct this structure. It's actually rather simple. So suppose we chose the ordering M, J, A, B, E. This may or may not be an ideal ordering, but then we start by creating a node for M. Then we create a node for John, and then ask the question, is John dependent on Mary or not? So is John dependent on Mary?
No,
Not yet.
only given, they're only independent given alarm.
Not yet.
Is John dependent on Mary? If Mary called, do you change the probability that John called?
Yes.
So they are not dependent, they are dependent,
Yes.
not independent, right? So therefore we will have an edge from Mary to John. I guess you're totally confused with dependence and independence. Intuitive. Mary called, then you increase the probability that John is going to call either which way. So John calls actually depends on Mary calls, so we add an edge. Now we take the next note. Is alarm dependent on John calls?
Yes.
Is alarm dependent on Mary calls?
Yes.
So we create two edges. Burglary. Is burglary dependent on alarm?
Yes.
Yes. Well, yes. It's not a
If
question.
alarm happened, then do you change the probability that burglary happened?
Yes.
So
If not,
burglary
we're
depends
paying
on.
ju- If not, we're paying the alarm.
It doesn't have to be causal. So now here is the point where we are not necessarily going causally in the order, but that still makes a valid Bayesian network. As I said, it is more intuitive to think causally, but you don't have to think causally. So burglary depends on alarm. Now, does burglary depend on John calls or Mary calls?
Both.
Not giving an error.
Given alarm. Exactly. So we just need to add one edge here because we can say this is yes, and the last question is what about earthquake? What edges should we add?
Alarm, very highly burglary.
Alarm and no, just alarm. Just alarm.
If we knew the very caught, then we would.
Well, if you're going to reverse order, you're going to pick burglary and then you're going to pick alarm.
That's what I'm thinking. We'll have to pick burglary and alarm. This is because
Earthquake and burglary are not independent.
right.
How?
Why aren't they?
Say if an alarm goes off, knowing the probability of whether or not a burglary occurred will affect the probability of an earthquake having occurred.
So again, it's the same intuition. So if alarm goes off and burglary did not happen, then I have a different probability of earthquake. And if burglary did happen, then I have a different probability of earthquake. So in fact, these are all related. But once alarm goes off, Mary calls and John calls are not bothering my earthquake.
So you're applying deseparation and Markov blanket and all those rules to create this graph at that point. You're saying if it's given that you have B, A, J, and M.
Right. So I mean, I am at the moment using only intuition to create this in a certain order. I'm not necessarily giving you a very well-defined algorithm, but the only point of the exercise is that if you have lots of variables, then you can create a Bayesian network by starting from one variable, thinking about the conditional dependencies from the previous variables, and keep going and adding the edges where the conditional dependencies hold.
So if burglary happens, most likely the alarm would have gone on, which means earthquake may not have happened.
Right.
So in this sense, just by knowing burglary, I can predict our earthquake.
Exactly. So I have to add this edge. If I know burglary, it still depends on the alarm what earthquake happened, but Mary and John are sort of.
So what are we trying to do here overall? So in the previous cases, we were given the edges and we were trying to figure out dependence independence, and here given dependence independence, we're trying to figure out the edges.
The network. Precisely. This is the intuition, and again, this is not an algorithm. This is just the intuition that how we can construct Bayesian network if we as people were constructing the Bayesian network. This is not a rule for learning an algorithm to construct Bayesian network from data, which we will discuss next class. So this is just an intuition about creating this network based on our own intuitions, based on knowing the conditional independences. Yes?
So what you're saying is that this network is equivalent to the one that we made up.
Right.
And it's just
And it has more parameters. So, because it has more edges. So this is not an ideal network, but this also shows that the variables need not be picked in the causal order. Even if you pick them in slightly different orders, they're going to get slightly different network. It will be still consistent.
So just from the original graph, if I said, hey, I have a burglary, given that I know that there's a burglary, what's the chance that there was an earthquake?
Yes.
That is still linked. The original network still gives you a link between the two. So,
No, those are independent.
but here it looks like they're
But the
independent.
probabilities will come out to be the same. If you compute the conditional probability distributions based on the previous probability distribution we had, we'll come back with exactly the same probabilities.
So in the original, just sorry, bear with me. In the original network, if I said probability of burglary given earthquake is equal to probability of burglary, is that the answer from the original network?
Yes, and this network doesn't say that.
This network doesn't say that. So how are they equivalent?
So, okay, so you are asking an excellent question. So if you wrote down all the set of conditional independences that this network has, and wrote down all the conditional independences that this network has, there will be some differences.
Right.
So it is not exactly equivalent.
So what makes a network equivalent?
If you add the probability distributions here, so if you tested for probability E given B, if you had the conditional probability distribution right, then your P of E given B will come back to equal to be P of E. But just by looking at the structure of the network, you cannot say that. So each structure encodes some conditional independences, and the conditional independences that are encoded in this structure are less than the conditional independences that are encoded in this structure. But if you test it for conditional independence or independence using the actual probability values, then you will get to the same answer. So that is what is happening into it internally. Marius.
So the idea is that any directed connected graph without cycles is good. We don't need the edges that are into it. Any directed connected graph without cycles is a Bayesian network.
It is, yes, absolutely. And we can take the same Bayesian network, change the order of edges, order of variables, and create another Bayesian network which will also have come up with the same probability distributions, may not be as compact. Yes.
What does it mean if it has a cycle?
There is no semantics. So there is no cycle here. This is not a cycle. If it's a cyclic graph, then the semantics is not clear because the influence is propagating back. So it's not allowed, essentially.
It cannot represent any kind of real
Consistent probability distribution.
So,
Yes.
so the cycle is actually a waste of memory. Is information that we don't need to keep because it's already defined by the other edges that are the cycle. That's why we made the cycle to compact the information basically.
Maybe we can say that. Basically, Bayesian network does not have a consistent semantics as soon as we have a cycle, because now the parents can be the children of the parents, and the probabilities.
The cycle is completely defined, so we don't need all the edges. They don't, yeah.
You don't need a cycle to represent it.
Right.
So can we
We
say,
have only certain values in a cycle. There's a redundant information, basically.
Okay, so let's move from here, and the point that I want to next make, yeah, Abhishek.
so can we say if we choose the order of variables in the causal effect manner, then we get optimal Bayesian?
It's at least easier to fill in.
It is definitely. I wouldn't go as far as saying that we will get an optimal order. I think finding the optimal order for in which order we should consider these variables is NP hard at least. But it will definitely be easiest for us to do it, because we can we could see that it is quite tricky to figure out what conditional dependence is, what is a non-causal order.
What I meant with the cycle between alarm, burglary, and earthquake, we can eliminate any edge. It still will basically have the same information.
No, this particular thing you need all these three edges.
The three edges are defined between themselves.
No, this is not a cycle, because this is not going back to alarm. The influence is flowing like this.
Yeah, but if I don't know if any of them is not given, they are all interdependent. So,
That's true. That's what I was saying, why you would add if you added earthquake last, you would only add edges to alarm because the information in alarm is already
so
encapsulates
everything is
Mary and
acceptable.
John. So you wouldn't have edges for Mary and John because that information is already in alarm.
But then we didn't add those edges, right?
But
Well,
we can if we want.
That's why you didn't add those edges.
Right.
Yeah.
But I think he's saying something else.
It's not a problem. We can add whatever edges we want as long as it's not a cycle. We can add an edge between Mary and burglary.
But that will not be necessary. Are you?
As long as there's no edge between alarm and burglary.
Fair enough. So basically what you are saying is that you can add another edge here.
Yeah.
And yes, you are right. But it will be a wasted edge.
Yeah,
So,
but then we'll remove another edge. So then we'll not waste anything.
Is there any edge that you can remove?
No, I don't think
So
so.
I can add an edge between Mary and burglary and remove the edge between alarm and burglary. The network will be as expressive as before.
That's not true. Because,
You have to add an edge from John to Burglary.
exactly, you'll also have to add an edge from John to burglary.
I don't have to because I have a path between them. So I can, they are still dependent to that path.
Well, that path is not necessarily a path. You have to
No,
choose
so
from that
basically,
perspective.
I would say we should do this as homework, but if you compute all the conditional independences that hold in the first network, and then what you do is that you add an edge from Mary to burglary, remove this edge, then it will encode a different set of conditional independences. There will be a conditional dependence in this new network that will not be present in the first network. So that I strongly believe it. Let me do this homework and give you the answer next time or on email. Okay, so having gone through the independence and dependence, now we come to the fun part, which is why are we doing this, right? So remember that long time back we had this diagnosis task, which said if my engine doesn't start, then what is the failure? What could have gone wrong? There we had no notion of probability. So there we had no notion of we said there may not be any gas in the engine, or the fuel line may not be okay and things like that. But we had no distribution of what is more likely, in what order we should investigate this, and so on, because that was a logical framework. All the things that we can do in a logical framework, people have done and more in Bayesian networks, and we get a much better diagnosis or much better results because we have the notion of what is probable and what is less probable. So here is a simple Bayesian network for car diagnosis. And again, there are hidden variables that we can't observe. There are some variables that we can observe. This is the evidence. And we have to figure out what is wrong. And when we figure out what is wrong, then we will be able to even also assign probabilities of what is more likely to have caused this failure and what is less likely to have caused this failure. And so we will be exploring these diagnoses in that order. This is extremely, extremely common. These kinds of Bayesian networks happen over and over and over. So for example, this is a Bayesian network for car insurance. And it says that age of a person determines whether they are good students, age of a person determines their driving skill, their make and model determines the ruggedness of the car, whether they have anti-lock brakes determine whether they will be in an accident, and so on and so forth. And so these, based on this framework, you can estimate a cost of the medical cost, a liability cost, property cost, and based on that, you can assign them an insurance rate. These kinds of things happen over and over, and we talked about medical diagnosis, where you have your symptoms, and there are multiple things that are going on in your body, and eventually you observe the symptoms, and you want to predict what the diagnosis are. Another example is sensors, and you get some observations, and you want to predict the rest of the state of the system. For example, you can observe the highways and the traffic on the highways, on the main roads, but you cannot necessarily observe the traffic on each individual road. But by observing the traffic on the highway, you may be able to predict in main road, you may be able to predict the traffic in nearby roads. Very common. In fact, Microsoft also had, in Eric Horvitz's group, Microsoft also had the system where they had sensors in various roads, and they were able to predict what would be the traffic in other roads, and based on that they will route you, right? Image segmentation, or a lot of image applications. I think, I have a list of applications. Basically, as soon as you have many variables which are interacting with each other, by knowing one you have some information of the other and so on, you start to use, the first thing that should come to your mind is Bayesian networks. Okay. Once you get past this hurdle of independences and so on, this would be the way to go. Therefore, this is an extremely valuable thing to learn and put some energy in. So, a lot of computational biology is Bayesian networks. A lot of natural language processing is Bayesian networks. What is natural language processing in this case? Part of speech taggers. You read a sentence, you want to figure out whether this is a verb, this is a noun, what is an adjective, what is the part of speech for each of the words. That becomes like a Bayesian network. Why? Because a noun is typically followed by a verb. A noun is typically preceded by an adjective or a verb. By knowing these dependencies, if I know that something is a noun, I have some idea of what is going to happen next, what happened earlier. So there are independences. We were talking about image segmentation. Suppose you have an image of a cow. By knowing that this pixel is an image, is part of the cow, it is much more very likely that all the neighboring pixels are also parts of the cow. So we can do segmentation better by modeling these dependencies between all pixels, and so on and so on and so forth. Basically, any system which has many variables, where by knowing one variable, you are influencing a subset of other variables, and is in an uncertain environment, which is usually all of the world, the first thing that comes to mind is using Bayesian network technology and inference on top of it, which we are going to learn next. You have a question?
So how do we generate those graphs programmatically?
We will talk about learning these Bayesian networks and how can we generate those Bayesian networks using data. We will talk about that probably next class, but we will talk. Yes, Marius.
I have a question. So from the description it sounds, is a Markov decision tree basically a Bayesian network with at least one cycle?
Markov decision process which we did last time.
Markov, we could do that loop. So it's basically like a Bayesian decision, like a Bayesian network with one cycle, so that we can do that.
So that is not true, and the reason is that Markov decision process is a temporal model. Their time is increasing. So when we say S and S prime are related with an action, then what is happening is that we are talking about the variables at time t and variables at time t plus 1. So even if
It's still a tree with probabilities between nodes. It's the same structure in the end. So Markov decision tree and Bayesian networks have the same general structure, just that Markov decision tree have at least one cycle.
No. So there are a couple of things. First of all, the goals of the two processes are completely different. So for Markov decision process, the goal is to find an action to execute in a state. Whereas the goal of Bayesian networks is to find a probability of a certain query given the evidence. So when we use Markov decision process and we want to use the power of Bayesian networks, we have to first create a Bayesian network which varies in time. The model for that is called dynamic Bayesian network. So that is probably in your chapter 15 and you can have a look at it. And then in order to create a full Markov decision process, you have to add action nodes and you also have to add utility nodes. When you add that, it becomes influence diagram. And even in influence diagram, there is no cycle. So then Markov decision process is one step further to that which has cycles. So in some sense what you are saying is right, but there are multiple layers of abstraction that we haven't discussed. So it's very hard for us to communicate these so many layers. But it's a fascinating field and we won't get into dynamic Bayesian networks or influence diagrams, but if you're interested, you should definitely look at them because that will be a way to get to Markov decisions. So first of all, we realize that conditional probability tables grow exponentially with the number of parents. But what happens when we have continuous valued parent or child? How do we handle that? What are the various kinds of distributions that we can specify compactly? So one of the distributions is if it's deterministic, like North American is exactly equal to Canadian or US or Mexican. That's a distribution that we can specify compactly. We don't have to think too much. This can also happen in a continuous domain. But when you have real probability distributions, if you have n parents for a certain node, then you can have 2 to the power n probabilities in that conditional probability table. Right? So one of the common canonical probability table is called noisy OR. And that says that my parents are independently affecting the effect. Here's an example. Fever may depend on cold, fever may depend on flu, fever may depend on malaria. If I had to create a full probability table, then I will have 8 values in this conditional probability table, one for each value of cold, flu and malaria, false, 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 true, and so on. Now that may be too much if a certain symptom can be affected by too many diseases. So what people typically do is that they will create a noisy OR network, which means that they will only remember the direct influence on fever for one disease at a time or one parent at a time, and then assume that all of those diseases are independently affecting the symptoms, which means the following. So, if there is no disease, let's say there is no fever. If there is only malaria, let's say fever is 0.9. If there is only flu, let's say fever is 0.8. And if there is only cold, let's say fever is 0.4. These are the values we are given. And now based on these, we can estimate the others using the noisy or assumption. So for example, if both flu and malaria are true, then we will do the following reasoning. Then it's only 0.1 probable that we will not have fever because of malaria, and it's only 0.2 probable that we won't have fever because of flu. So it's only 0.02 probable that we won't have fever because if we have both of them, and therefore it's 0.98 probability that we will have fever if we have two of these diseases. It's an approximation, but that allows us to represent this 2 to the power n sized conditional probability table by using only n parameters. In some situations it works, in some situations this independence assumption may be wrong. Yes.
Why is it approximation? Why is it approximation?
This is an approximation because we are making the assumption that the failure of the symptom is happening independently. So the actual probability of whether we have fever or not, if we have both flu and malaria, may be probably even higher because flu and malaria may even interact in our body and increase the probability of fever or decrease, whatever it is. But we are making the assumption that they are not interacting and we will independently compute it. Now let's talk about hybrid systems. So we may also have variables which are continuous. And this is just a feel, we don't have to go deep into it, but we should know that this is possible. So for example, this is an agricultural scenario. If I'm a farmer and I got some subsidy in buying seeds or fertilizers and so on and so forth, and then I got some harvest, that will determine what the cost is in which I am selling my product. And that cost in which I am selling my product determines whether the next person is going to buy my product or not. So the subsidy is a Boolean variable, whether the person is going to buy or not is a Boolean variable. Harvest and cost on the other hand are continuous variables. Now, whenever we see continuous variables, we can always try to discretize them and use whatever we know about discrete variables. Often it's a bad idea because it becomes, the CPTs become really large and the errors become large. So usually what people do is they study finitely parameterized canonical families. So they assume that the distribution will have certain shape and they will be parameterized by one or handful of parameters. So let's take an example. If you have a continuous child for a continuous parent, then you can create maybe a Gaussian distribution. Right? So you can assume that my cost depends on the harvest with around some mean and with some standard deviation. And you may have to do it for all cases of subsidy. So subsidy true, you will have one Gaussian, and subsidy false, you may have another Gaussian. That depends on the harvest edge. Gaussian is one model, you can have other models. What about discrete children and continuous parents? So again, the intuition here is, I have a continuous parent cost, how will I represent the conditional probability table of whether the person is going to buy or not? So here, if the cost is too high, then it is unlikely that the person is going to buy it. If the cost is too low, it is quite likely that the person is going to buy it, and somewhere in the middle there will be a probability distribution change from buying to not buying. So we can say that maybe this should have been, the way I am describing it should have been in the other direction, but as the cost increases, the probability of buying goes to 0, and if the cost, this is buying equal to false, right, exactly. So this is the probability that buying equal to false given the cost. So as cost increases, the probability that buying equal to false is very close to 1. And so you need some representation of a function which has this kind of a shape. And so one of this representation is the integral of Gaussian. There are others like sigmoidal. And the intuition there is that most likely it's a hard decision, but we don't know the boundary of where this hard decision is. So we put a noise on top of it. So that's an intuition. But again, the point is, the main point that I would like you to take with this representation business is that whenever we have continuous variables, we have to think carefully of what the shape of this distribution, conditional probability distribution lies, create a parameterized distribution, and then work with it. Typical representations are Gaussian.